Let's go over some concepts and ideas from section 3.1, determinants. So a determinant can be given by a formula or a definition where we expand along the first row. The elements in the first row of an n by n matrix could be a11, a12, etc., all the way to a1n. And the determinant is going to be given by the product of that and the determinant of the minor matrix. And then we add all those together with alternating signs, and we get the determinant of the whole matrix. Now, we can rewrite this formula a little bit neater if we define a function for the cofactor. And the cofactor function is going to be given by -1 raised to the I plus j times the determinant of the ij minor matrix. And that's going to be the matrix when we cross out the ith row and jth column. And so the determinant can be given in a more compact form, a11 times c11, the cofactor, plus a12, c12, etc., going all the way up to a1n, c1n. Now this is a cofactor expansion on the first row as defined in our determinant. But we actually have a theorem that says we can expand along any row or any column. And so given those definitions with the cofactors, we can expand along the ith row if we want. And this ai1, ai2, ain would be all elements in the ith row. And then the ci1 would be the cofactor when you cross out the ith row and the first column, etc. You can also expand down the jth column, any column you want, whatever is convenient. Now, in an example that we're about to do, I think the ideal situation is to look for rows or columns that would have a lot of zeros. So if I look down in this 5 by 5 matrix, I can see that the fourth row is a good row to expand on, and it turns out that the fifth column is also a good column to expand on because there's a lot of zeros. So let's go ahead and do this example by expanding on, well, it doesn't matter, let's expand on the fifth row. Just to get us going, we have to remember our pluses and minuses. So if you always start with a plus, minus, plus, minus, plus, minus, plus, minus, plus, you can assign each element a sign, and if we can confirm this by saying that this 0 over here is in the first row and the fifth column. And so remember that the sign is -1 raised to the I plus j. So this is -1 to the 6th power, which is positive. And then it follows that everything else is going to alternate after that. Okay, so let's expand through this. We're going to get this to be equal to, well, 0 times, this would be A15, and the first column, or the first row and the fifth column. The expansion here isn't going to matter. Let's call it C. I'm sorry, let's call it determinant. So determinant of A15 plus 0 times the determinant. Oops, this should be a minus, so I'm kind of doing a step back from the cofactors. I'm using the original definition. And then the third element is going to be 1, and now we're going to have to find the submatrix or the minor matrix after we cross that out. So we have a 6, 3, 2, 4, 9, 0, minus 4, 1, a 2, 0, 0, 0. Looking ahead, this would be a good place to expand. 4, 2, 3, 2. And then, so we have 0 and then another 0 that I'm not going to worry about writing. All right, so that's the first cofactor. Now I want to take a look at this and expand because I want the determinant of this matrix. And I want to think about expanding on the third row. So let's expand on the third row. And if we expand on the third row, let's keep this 1 here. And now let's worry about the determinant. So we got a plus minus plus. So this starts off with a plus, and this is going to be a 2 times, and everything else is 0. So let's just remember that everything else is going to be 0. So let's not worry about that. So I cross out the third row in the first column because that's where 2 is. And then the submatrix I have left is a 3, 2, 4, 0, negative 4, 1, and then a 2, 3, 2. Okay, so now I want to continue to work on this, and I would need to find the determinant of this. Now I can do the same thing. It looks like I would be interested in expanding in the second row. So let's expand on the second row. And this thing is going to be a 1 times a 2. And now I want to get ready to expand here. So I have a plus, minus, plus, minus. So I have a 0 that I'm not worrying about. And then I have a plus, and then this is a negative 4. And now the submatrix, if I cross this out, is going to be a 3, 4, 2, 2. And then I have a minus 1. And the submatrix that I get, if I cross that out, is a 3, 2, 2, 3. Okay, so now we should know the determinant of a 2 by 2 matrix. So let's kind of round everything together here. 1 times 2 is 2, and then we have a negative 4 times, here I have a 6 minus 8. So positive 6 minus 8, and then I have a minus 1 times, I have a 9 minus 4. So if we simplify this, we're going to get 8 minus 5 is 3 times 2 is 6. So it looks like our final result is going to be 6. Okay, so that's how we expand on a particular row or column, and that's how we can find our determinant. Now, it turns out that if we have a triangular matrix, our determinant would be easy to compute. It's just going to be the product of the diagonals. So imagine taking 4 and then crossing out our row and column, and we have a submatrix, which is 7, 2, minus 5, 0, negative 3, 0, 0, 0, 1. But then if we think about expanding on a particular row or column, let's expand on the first column, then we have 7 times minus 3, 0, 0, 1. And then this is already a 2 by 2 matrix, so we can just find the determinant here. So that's 4 and 7 and negative 3 times 1. And then since this is supposed to be an upper triangular matrix or a triangular matrix, we have one of these, in this case both of them are 0, and so there's no wings to subtract, and so this just turns out to be the product of the diagonals. Okay. Now one last piece of information in this section would be taking a look at determinants of elementary matrices. And so an elementary matrix remember, are matrices that that come from the identity element, and we perform an elementary row operation. So in this case, for example, what we did was from the elementary matrix, we multiplied row 2 by k, and then we added it to row 3. And so that's the resulting matrix. Now the curious thing is we want to find the determinant of this. So 1, 0, 0, 0, 1, 0, 0, k1. Let's find the determinant of that. Let's expand on the first row or first column. So let's go on the first row. We have 1 times 1, 0, k1. And this is just going to be 1 minus 0. So that's just going to be 1. So in this particular elementary matrix, our determinant is equal to 1, which is the same as the determinant of the identity matrix. Now let's take a look at what happens if we switch a row. So here we switched row 1 and row 3. And so what happens when we switch row 1 and row 3? Let's expand through the first row. So 0, 0, 1, 0, 1, 0, 1, 0, 0. Expanding on the first row, we're going to get 0 minus 0 plus 0. So we have a plus 1. And the submatrix is going to be 0, 1, 1, 0. And the determinant of this is 0 minus 1. So this becomes a negative 1. So when we do a switch, it looks like we're going to come up with a negative 1, which is a negative of our identity matrix determinant. Okay, let's do one more. In this case, we took a row and then we multiplied it by a constant. And so that's another elementary row operation. So again, we can expand on anything we want. There's a lot of zeros, so let's expand on the first row. We got 1, 0, 0, 0, k, 0, 0, 0, 1. And the determinant of that expanding on the first row is going to be 1 times the determinant of k, 0, 0, 1. And that's just equal to k. So it looks like if we multiply a row by a constant, then the determinant of that particular elementary matrix is k. So this is going to play an important part for us in our computing determinants for larger matrices, and we're going to want to remember this. Okay, so that's a summary of 1.3, or I'm sorry, this is a summary of 3.1. We'll take a look at 3.2 and 3.3. We're in section 3.2, and this section starts off with a theorem that says that if you have a square matrix and you perform an elementary row operation, your results are going to be predictable. So an elementary operation where you multiply one row by a number and then add it to another row will leave your determinant to be the same. If you take two rows and you switch them, then your determinant is going to be the negative of what you had before. And if you take one of the rows and multiply it by a constant, then your determinant is also going to be multiplied by a constant. Now we saw this in our last section, but we saw just the elementary matrices. So we could take a look at the actual row operations that happen on an example matrix and take a look at what happens to the determinant. So here's our example. We're going to do some row operations on this. First of all, let's just say that you have a determinant of A is equal to 84 in this particular example. And so let's do a row operation where we multiply the first row by -1 and add it to the third row. And so if we multiply the first row by -1, add it to the third row, our 4's will disappear, our 2's will disappear, and then 0 plus -3 will remain -3. So this is our resulting matrix. And so now let's imagine taking the determinant of this. I think this is easy enough to do. We can expand on the second row. We get a plus, minus, plus, minus, plus. So this is going to be a positive 1 times the resulting matrix left. That's 4, 0, 0, 0, 0, and -3, 0, 7, 2. And here we can expand on anything we want. Let's expand on the first row. So that's going to be 4 times 0 minus 3, 7, 2. And so this is going to be 4 times negative 7 times -3. So this is going to be let's do a parentheses around that. So this is going to be 4 times 21. And we multiply that, it's going to be 84. So 84, as we predicted, by doing this particular row operation, it does not change your determinant. All right, let's do the next one. What if we take our first row and multiply it by 1/2? So our first row used to be 4, 0, 0, 2. Our resulting matrix is going to be 2, 0, 0, 1 in the first row. And so if we imagine taking the determinant of that, let's expand on this row again, the second row. And so this is a plus. We're going to get a plus 1. And then our submatrix is going to be 2, 0, 0, 4, 0, -3, 0, 7, 2. And then we'll expand on the first row. So the first row is going to be positive 2, then 0, -3, 7, 2. And then again, this is going to be a positive 21 times 2, and then times 1. So this becomes a 42. Which is half of 84, which is what we had before. All right, our last example, this is actually a row switch, not a plus, is taking our original matrix A, and then we're going to switch the second and fourth rows. So if we switch the second and fourth rows, this is what our resulting matrix is going to be. And let's expand. We need to expand on something. Let's expand on the second column because that has a bunch of zeros. So this is a plus minus plus. We got a positive 7. And then our resulting matrix is 4, 0, 2, 4, negative 3, 2, and 0, 0, 1. And so with this, I would expand on the last row. That's positive, negative, positive, negative, positive. So that's going to be positive. And then we have a 4, 0, 4, negative 3. And then this is going to be 7 times 1 times, this looks like it's a negative 12 minus 0. And 7 times negative 12 is negative 84. So it's a negative of our original determinant, of the determinant of our original matrix. So that shows us that if we know the determinant of a matrix and then we do row operations, then we can anticipate the determinant of the new matrix. There's a few more theorems that we need to just mention. This theorem can be added on to our inverse matrix theorem. This is another condition for a matrix to be invertible, and it says that if A is invertible, then determinant is equal to 0, and vice versa. If determinant is equal to 0, then the matrix is invertible. So that can continue on with our A through O or P or whatever, however many parts we have in that theorem. Another couple of important theorems. The first one is that the determinant of the transpose is equal to the determinant of the original matrix. And we can kind of see that because we're able to expand on any row and any column, and we're going to get the same results. So I won't talk much about that, but the last one is the most important one, and that is the determinant of a product is equal to the product of the determinants. Now, the product here is a matrix product and does not commute. This one over here is a regular product, and so we can switch the order on this side if we want. Not that we care, but in case we're interested, this is just a regular product. For this, I wanted to take in the example or what they have in the textbook. And what they have in the textbook is not a proof, but a way to verify different size matrix. And what they do is they randomly select matrices or numbers for matrices A and B. You can do a 2 by 2 and 3 by 3 or 4 by 4. And what they do is they compute the determinant of A and determinant of B and multiply it. And then they compute the product matrix AB and find the determinant of that. So you can see that regardless of what matrix we come up with, the products in the theorem will work out. We can do this for a 3 by 3 matrix as well, and a 4 by 4 matrix, if we can see it. So I like the idea that you can randomly generate these matrices, and regardless of what size the matrix would be equal to, randomly generated, we find the determinant of A and the determinant of B and multiply it, and then they multiply the matrix here and find the determinant of that, and it turns out to be the same. So the multiplicative property will hold for matrices, or there's a special multiplicative property for matrices. Now, how is that helpful? Well, I think what we can do is we can take a look at our matrix over here again. And let's say we didn't know that this matrix was equal to, the determinant of this matrix was equal to 84. So what can we do? To find the determinant of this matrix? Well, what if we do some row operations to make it look like a triangular matrix? We know the determinant of a triangular matrix pretty easily. And so let's go through that process. So A is equal to this. What if we do a row operation where we, well, let's do the row operations that we did earlier. Let's take row 1 and multiply it by -1, add it to row 3, and then what we get there is 4, 0, 0, 2, 0, 0, 0, 1, and 0, 0, minus 2, and then 0, 7, 2, -5. Okay, now let's carry on here, continue, and let's switch the second row with the fourth row. So we have 4, 0, 0, 2, and then now we switch, we got 0, 7, 2, -5. We have 0, 0, minus 3, 2, and then we have 0, 0, 0, 1. And now let's do one more operation. Well, I don't know if we need to do one more operation. I was going to do multiply the first row by -1/2, but we don't need to do that because it looks like we have an upper triangular matrix already. So what did we do to get here? So let's call this matrix B, and then how did we get to matrix B? So we took A and we did an elementary row operation on A where we added, we multiplied the first row by -1, and then we added to row 3. Oops, there's a 1 here, and 0, 0, 0, 1. So that's EA. That's our elementary row operation. And after that, we switched. We switched the second row and the fourth row. So this particular matrix would look like this: 1, 0, 0, 0, 0, 0, 0, 1. That's our fourth row. 0, 0, 1, 0, and 0, 1, 0, 0. That's our second row. Second and fourth row were switched. So our B is essentially equal to this. So how's that helpful? Well, we can write B now as a product of these three matrices. And we know the determinant of B, because it's a diagonal, or because it's an upper triangular, it's going to be the sum of the diagonals. So that's -84. And this is what we're looking for, question mark. We know the determinant of E1, since we're doing this first elementary row operation where we multiply a row by something and add it to another row, will remain the same. And since this elementary row operation came from the identity matrix, the determinant of that will remain 1. And then determinant of a row switch will give a -1. That's a -1. And so we have -1 times 1 times A. Oops, write that over here. And we get -1 times 1 times A is equal to negative 84. And so A, the original matrix that we're looking for, determinant of A, is equal to positive 84. So what we can do is we can do a set of elementary row operations to write it in row echelon form. So when it becomes row echelon form, it becomes an upper triangular matrix. And then the determinant of that will just be the product of the diagonals. And then all those row operations that we did have their own determinants. And according to the multiplicative property for determinants, we just need to keep track of these elementary row operations, and they're either going to be 1 or -1 or some constants, depending on if we multiply a row by a constant or anything like that. And then that's going to help us find our determinant. Okay, so that's how the multiplicative property can be useful, is that we can write our matrix in row echelon form, and then take into account all the other elementary matrices that we need to consider so that we can find the determinant of our original matrix. All right, so that's really the highlight of section 3.2. We are in section 3.3, and let's take a look at some ideas discussed here that extend determinants. First, there's Kramers rule. It says here that if we have an invertible n by n matrix and we want to know what x values or what x vectors send that matrix to B, then we can find the solution by finding each individual x and then finding the determinants. First, the denominator is going to be the determinant of the original matrix A, and then the numerator is the determinant of the matrix A with the ith column replaced by B. So that is going to be our main part of this theorem. So let's take a look at an example. Here's an example of a system. We can say that A is going to be 1, 1, 0, minus 3, 0, 2, and 0, 1, negative 2. Those are the coefficients of the x1, x2, and x3 values over here. And so the system is really saying that your A and then your x1, x2, x3, when you apply it to the matrix A, what values of x1, x2, and x3 will send that matrix to 3, 0, 2, the vector. Okay, so we're going to be interested in finding the determinant of A first of all. So let's find the determinant of A. Let's take advantage of some of the tools that we had about expanding over a particular set of values. Let's go with the first row, and if we expand through the first row, we will have a 1, and then the submatrix here is 0, 2, 1, negative 2. And then we have a negative 1, remember alternating signs, and then the submatrix here is minus 3, 2, 0, negative 2, and then we have a 0 times the submatrix of that. And so what we have is 1 times negative 2 minus 1 times positive 6. So it looks like our value is, our determinant is negative 8. Okay, so that's a good start. Now let's find the determinant of these other matrices. So A1 of B, they're calling it here, is going to be the matrix A1. So let me write down the matrix A1 and I'm going to erase something. after I write it down. And what we want to do is we want to replace the first column by the matrix B, or the vector B. So let's get rid of the first column, and let's replace it with the vector B, which is 3, 0, 2. Okay, so this is our A1 of B, and let's go ahead and find the determinant of that. And it looks like our second row has 0, 0, 2, so I'd like to expand on that. We have so the determinant of A1B is going to be equal to, this is a plus, this is a minus, minus 0, plus 0, and then more importantly, this has a negative sign as your sign of this element. So we have a 2, and then a determinant of 3, 1, 2, 1, and that is minus 2, 3, minus 2 is 1, so that's just going to be negative 2. Okay? So now that we know that, we can find your x1 value, the x1 value that we're looking at here. So x1 will equal to, let's do this in a different color here. X1 will equal to negative 2 divided by our original determinant of A, negative 8. So x1 is equal to 1/4. Okay, now let's go back and continue with finding A sub 2 of B. And again, we write down the A matrix, and then we're going to replace the second column by the B vector. So we'll write down the others, and the second column is going to be replaced with 3, 0, 2. And now we go ahead and expand again to find the determinant. I don't think any of them is more favorable than another, so let's expand through the first row. We have determinant of A2 of B is going to equal to times the submatrix, determinant of the submatrix 0 and negative 2, 0, 2, 2, negative 2, minus 3. We have minus 3, 2, 0, and negative 2, and 0 for our last term. So we're going to get 1 times 4 minus 3 times positive 6. And here we have 4 minus 18, so that's negative 14. Okay, so now that we have that, we will so the determinant of this matrix, expanding on the first row, will be 1, and then the submatrix here is 0, 2, 2, negative 2. We have a minus 3. The submatrix there is going to be minus 3, 2, 0, and negative 2, and then 0, and then that doesn't matter what the submatrix is. So we have 1 times negative 4 minus 3 times positive 6. So that's negative 4 minus 18, that's negative 22. Okay? So now we have our second solution. X sub 2 is going to be equal to negative 22 over negative 8. So that's a positive 11 over 4. That's your x2 value. Okay, let's carry on to the last one. We have a sub 3 of b, and we get 1, negative 3, 0 going down the column, 101 and 302. And the determinant of this a sub 3 of b is going to equal to, looks like we can expand on the second row. We start off with a positive here, and this is a negative here. So it's going to be negative 3, and then cross out the row and column. We have 1, 3, 1, 2. So this is going to be a 2 minus 3. So this is going to give us positive 3 times negative 1, negative 3. Okay. So lastly, that would give us our solution for x3. x3 is going to equal to minus 3 over negative 8. So that's just 3/8. Okay. So that's how we use Kramers rule. We've seen it, I think we've seen it done for a 2x2 matrix, but here's an example of 3x3. Let's continue to use Kramers rule with another example here. This time they're throwing in some variables, some unknown variables, some unknown quantities. And this would be an example of Kramers rule in 2x2. So let's take a look at our A vector, or our A matrix. So the A matrix is going to involve a variable S, 2s, 3, and 6s. And so the determinant of that is going to be 6s squared minus 6s. So that's our determinant. And now let's find our modified matrices A sub 1 of B, and this is the B vector here. A sub 1 of B is going to equal to, well, let's put it here. It's going to be the A matrix where the first column is going to be replaced with a B vector. So that's a 2s and 6s, and then 1, negative 1, 4. So the determinant of this 2x2 matrix is going to be negative 6s minus 8s, and so this is negative 14s. And then if we put that in the numerator here, our x1 is going to be equal to negative 14s divided by 6s squared minus 6s. I suppose we can do some simplifying. We can factor out a 6 and cancel a 2 from the top and the bottom. We can also get rid of an s. So it'll look like we negative 7 divided by 3 times s minus 1. So this is our x1. And then now we go A2 of B is going to be the matrix S3 in the first column, and then negative 1, positive 4 in the second column. So that the determinant of that is going to be 4s minus negative 3. So that's 4s plus 3. We have our x2 solution, 4s plus 3 divided by 6s, and then s minus 1. All right, so that's a quick application to Kramers rule. You might imagine that it could be a little bit difficult to solve for this with these variables s's around, but with Kramers rule it becomes an easy formula and easily computable. All right, let's move on. They introduce another theorem here, another way to find the inverse of a matrix. Now, this is a neat formula, but it's not usually something that people use because it's not. It requires a lot of computation, and so I think it's just here for show and not really for practical purposes. Well, let's take a look at it. So the adjugate, or sometimes the classical adjoint matrix, is the transpose of the matrix of cofactors. Now, if you remember what a cofactor was, a cofactor, let's write cofactor, is C sub ij, and this is equal to the sign of the position of the matrix, so the I and jth position. You add them up and it's positive or negative depending on where you are in the matrix, times the matrix Aij, which is a smaller matrix. The determinant of this, sorry, let's fix that up and make sure it's the determinant. So the determinant of Aij, and Aij is a smaller matrix when you cross out the ith row and the ith column. Ith row and the jth column. So the idea here is that you need to find each of these for each of these values over here, and then make a new matrix out of that, and then find the determinant also. So it seems like it's a lot of work, but it might be interesting to check out and see. Let's see what we can do. If we can do this quickly. Let's find the determinant of A first. And here it looks like it would be good to expand on the first column actually, or the last row. Let's go to the first column. We got 5, and then you cross out the first row, first column, you get, oh, you know what? We don't even have to do that. Sorry. Because looking at this is a triangular. So because this is a triangular matrix, we can just multiply the diagonals. So 5 times 1 times -1. So that's -5. So your determinant is -5. Now imagine we're going to have to find the cofactors. And so, like, what are the cofactors? Let's start with the first one. So C11 is going to be, according to this, it's going to be equal to +1, because this is in the 1, 1 position. So 1 plus 1 is 2. -1 to the second power is +1. And then we need the determinant of the cofactor, or the smaller matrix, the minor. So that's 1, 0, 3, -1, and that just is equal to -1. So C11 is equal to -1. We want C12. So this is going to be this position, the 1, 2 position. And so you imagine crossing out the row and the column. And first of all, the sign is going to be -1. And then crossing out the row and the column, we have -1, 0, -2, -1. And that's equal to negative is positive, with a -1 that's -1 again. C13, we're now in the third column, so this is a +1 as the sign, and then the determinant of the smaller matrix when you cross out that position, row, and column. We have a -1, 0, -2, -1, and that gives a +1 and +1. All right, so let's continue on. This doesn't seem so bad. Let's go in the second row now. C21 is going to be and what we have in that position is positive, negative, so this is a -1. And then we cross out the row and column, so 0, 0 on top, and that's going to knock out the determinant because we have a row of zeros, so that's going to be 0. C22 is +1, and then that's this middle term, our middle position, so we cross everything out. We got 5, 0, -2, -1, so that's 5, negative. And C23, which is going to equal to -1. And then the submatrix for this is going to be 5, 0, -2, +3. So that gets a 15 with a negative. Okay. So one more row. C31 is going to be a positive value. Sorry, positive, negative, positive. Yeah, so it's positive value, so +1. And then the submatrix is 0, 0. Again, we have a row of zeros, so that's just going to be 0. C32 is going to be -1. And then cross that out, we get 5, 0, -1, 0. 5, 0, -1, 0. And same with the rows and the columns. If you have a row or a column of zeros, that's going to be 0. And then the last slot is going to give us a positive value. And then the submatrix is 5, 0, -1, 1. 5, 0, -1, 1. So that's a +5, and that's it. So I purposely so that this is the row expanding on the row going down as a column, but since we have to take the transpose of the matrix, we're going to transpose it like this anyway. So this is really, these are going to be the column values. So our A inverse is going to be 1 over -5, and then we have -1, -1, 1, 0, 5, -15, and 0, 0, 5. Okay, so that's not the most efficient way to find the inverse, but there's some nice theory behind this idea of the adjoint matrix, or the matrix of cofactors. Okay. The next idea is to take a look at these, the geometry of vectors. So if A is a 2 by 2 matrix, an area of parallelogram determined by the columns of A is equal to the determinant of A. And then they want to just make sure, sometimes the determinant's negative, so they want to take the absolute value to make sure you're looking for the area. So let's take a look at this example. And here we have points that make up the parallelogram. So we have -2, 0 over here. We have a 0, 3, 1, 2, 3. We have a 1, 3, 1, 3. And then we have a -1, 0. So it looks like this is a parallelogram. And what you basically want to do is you want to find a vector, 2 vectors that would span this parallelogram. So it looks like we can find a vector connecting these 2 points over here. and we can find this vector connecting those 2 points over there. So these 2 points are both points where the y-axis is 0, and so it looks like it's just going to be 1, 0 if we subtract it. So minus 1, oops, let's get rid of that. Minus 1 minus negative 2, and 0 minus 0. So that vector would be 1, 0. So that's one vector. The other vector connects this point and this point, 0, 3. So if we find that vector is going to be so this is the head minus the tail. So we get 0 minus negative 2 and 3 minus 0. So this gives us a 2, 3. So those are the 2 vectors. We got 1, 0 vector and 2, 3 vector over here. So what they're saying is that if we just make column vectors out of this, 1, 0, and 2, 3, and it doesn't matter the order because switching the order of these columns will just make this positive or negative, and so we're going to take the absolute value anyways. And so the determinant of this, determinant of 1, 2, 0, 3 is going to be 3 minus 0, and this is already positive, so that's all there is. Okay, and it extends to 3-dimensional parallelograms, and now in 3-dimensional parallelograms they call it a parallelepiped. And so here we're assuming that in 3 dimensions we have 3 vectors that go out, and then if you imagine making a 3-dimensional parallelogram out of these 3 vectors, you get a parallelepiped, and the volume of that is the determinant of these matrices. Make columns out of them, 1, 0, negative 3, 1, 2, 4, and 5, 1, 0. And then we want to find the determinant of that. So let's do the cofactor. Let's expand on the first row. And so the determinant of this, just put straight lines here, is going to be positive 1 times the submatrix 2, 1, 4, 0 minus 0, so it doesn't matter what happens there, and then plus negative 3, and the cofactor there is 1, 5, 2, 1 submatrix. So we have negative 4 and minus 3 times 1 minus 10 is negative 9, and then we have 27, positive 27 minus 4, and that's positive 23. And then you would take the absolute value, but this is positive anyway, so we're looking at a volume of 23. All right, one more idea to cover here, and it's sitting in Theorem 10, and it says that the linear transformation determined by 2 by 2 matrix, if you send a couple of vectors from one space to the other space through a linear transformation, then the area of the transformed vector is going to be the area of the original vectors times the determinant of A. And so this transformation also works for parallelepipeds in 3 dimensions. So let's take a closer look to see what that means. We have these 2 vectors, and I'm just going to draw these vectors over here. So negative 2 comma 3, negative 2, comma 5. And so this vector in the original space would look like this, and so they would have a parallelogram that's in S. So this is let's say that this is your parallelogram S in the original space. Now the linear transformation T will send these two vectors to another set of two vectors. I don't know what exactly happens to these two vectors, but it could be a rotation, it could be a skew or scaling or reflection or whatever it might be. But it gets sent to another space here, and then it would create its own parallelogram. So the idea is that parallelograms get sent to parallelograms. And so to find this new area, that's the image of this parallelogram brought over to the new space. To find this area, we can just compute the area of the original parallelogram and then multiply it by the determinant of this matrix. All right, so let's take a look at the original parallelogram, and the area of S is going to be the determinant of the matrix made up by these two column vectors. And then we want to take the absolute value of this as well, so in case it comes out to be negative. So we have a negative 10 minus negative 6, and this comes out to be negative 4, but we want the absolute value of that. So the area of S is going to be positive 4. Okay. And so now we want to find the determinant of the A vector, or the A matrix, the transformation matrix. So the determinant of A is equal to 12 minus negative 9. So this looks like it's going to come up to 23. And so that's our determinant. If it was, again, if it was negative, you would make it positive. So the area of the vectors, the transformation, where you send this parallelogram over to the other space, is going to be 23 times 4. Okay. We can check this actually. Well, let's multiply this out. This is 12 carry 1, 8, 9, so 92. We can actually check this. Let's change colors here and check this. Let's actually find AB. And so that's this A matrix applied to this vector. So 6 and negative 2, that's 12. 12 plus 3 and negative 3, 9. Let's write that out. Negative 12 minus 9, that's negative 21. Oops, this should be 21. Sorry. So let's try that again. Now let's find the determinant of A. So A is going to equal to determinant of A is going to equal to that's 12 and then minus positive 9. So that's 12 minus 9. That gives us 3. So it looks like our determinant is equal to 3, and so the area of the image of our parallelogram that got sent over should equal to the determinant in absolute values times the area that we had. So that's equal to 12. All right, let's actually check that, and let's actually send these vectors over to see what they look like. So let's send the vector b1 over through this transformation. So that's 6, -3, -3, +2, and then our vector -2, 3. So this is going to be -12 minus 9. I think this is -21. Oops, let's write that a little bit neater here. So this is equal to -21, and then we have the second component. That's a +6, +6 minus 6, and that looks like it's going to be 0. So the first vector gets sent to -21, 0. The second vector, AB2, gets sent to, so we'll do the same computation. So I have a -12 minus 15. So that looks like it's going to be a -27. And then the second row, that's going to give us a +6 and a +10. And so that's going to give us a 16. So it looks like our second vector is this. Now, these are our new vectors that's happening here, so I actually misdrew this. But if I were to draw it, one vector would be -21, 0. The other one would be -27, 16. So let's find the area of this. So area of the image should equal to -21 Let's double check our result by actually sending the vectors b1 and b2 over to this new space. So for that, we need to find out what AB1 is. And AB1 is going to be 6 minus 3 minus 3, 2. That's our matrix A. We're going to apply B1 to it, -2, 3. And so here's a, you can think about it as a matrix multiplication. So this is going to be -12 minus, and then here we have -12 plus -9, which is going to equal a -21. And so that's the first component. The second component is going to be +6 plus 2 times 3 is 6, so that's 12. So that's AB1. Let's find out what happens to B2. Let's find out where it gets sent to. So we got 6 and -2, so that's -12 plus -3 and -3 and +5 is -15. So this is going to equal to a -27. So that's the first component. And then now we have -3, -2. That's +6, and then 2 and 5 is 10. So that's a +16. All right, so our two new vectors are negative 2112. So one of these vectors should have been negative 2112, and then the other one should be negative 27, positive 16. So this drawing was a little bit off, a lot off, but we're just looking at it from a theoretical point of view. So now let's actually figure out what the area of this is equal to. So area of the image of your parallelogram, or your parallelogram S, is going to be the determinant, absolute value, the determinant of minus 2112 and minus 2716, written down like that. So we have negative 21 and 16, and then 12 and 27. So I'll do this in a calculator, and it looks like the result is going to be negative 12. We want the absolute value of that, so it becomes positive 12. So this is our result by looking at the image. This is our result by using the theorem, and you see that they're both the same. So that's not a coincidence. It's the theorem that says that the volume or area of an image of a linear transformation is equal to the area of the original vectors times the determinant of the transformation matrix. Okay, so that's the last of the ideas and theorems in section 3.3. Okay.